Hello everyone, Paul Stechik with NEPSI. This is NEPSI Tech Talk session number 29. Today we are going to be meeting with David Odeman from AMSC to talk about the AMSC's DVAR VVO STATCOM system. For those who may not have seen the previous Tech Talks, we had previously talked with Naren Reddy on Tech Talk 16 where he introduced what a STATCOM is. And then on Tech Talk number 26 we talked about hybrid STATCOMs, where we mix a capacitor bank or filter bank with a STATCOM system to extend the range of the STATCOM system to make it more price competitive. And that was Tech Talk session 26. Both of those are available on our YouTube playlist channel. So today we're meeting with David Odeman, and he will be talking about the VVO STATCOM. So Dave, thank you for coming on to the Tech Talk session. Maybe perhaps you can introduce yourself first before we get into your presentation.
Sure, and thanks for having me. So my name is Dave Odeman. I am currently the product manager for the DVAR VVO distribution class STATCOM. I have a background in engineering, in power electronics, as well as power systems, and I'm glad to be here.
Great, thanks Dave. Well, so this is a relatively exciting topic here. This VVO STATCOM system is a relatively new product offered by AMSC, correct? It's maybe a couple of years now?
Yeah, so the original launch was in late 2017. So it is one of our newer offerings.
Oh, that's great. All right, well, why don't you might as well get going with it. I'm going to maybe pop up and ask some questions as we move along. And I did forget to mention that the attendees of the presentation today, if you hit Matt up or myself up with a request for PDH contact hours, we can give you those at the end of the presentation. I'll give you a code at the end of this presentation to email that to us. All right, Dave.
Great. Yeah, so today I'm going to go through what we call a deep dive webinar on the topic of using STATCOMs, specifically distribution class STATCOMs, to address motor starting problems. We'll go through kind of three parts and start out with going into the physics of the problem and really kind of set the foundation for introducing the STATCOM solution. Then I'll run through principle of operation of the STATCOM and share some application and case study examples. So I'd like to start by sharing physical properties of the induction machine. So when we talk about a line start motor, we're really talking about line start induction machines. And we love induction machines because they're a very low-cost workhorse of the industry. They're very proven, but they do have a couple of, I say, side effects that we have to deal with. And one of them is that there is a substantial amount of inrush when that motor is, when the induction machine is started. So this chart here is showing the voltage versus locked rotor torque versus the inrush current of a typical Class B type induction motor. And what can be seen with the highlighted red section here is that very high inrushes of reactive currents are an attribute of the motor. So we're talking about 600% reactive current on a starting event. And if we kind of think about that in practical terms, so like a 500 horsepower motor, that would equate to somewhere around 3,000 kVAR of sudden reactive inrush current on that feeder. So of course, as that motor would go higher, that's even much higher kVAR loading. So and to the distribution feeder, that literally looks like a step function increase in reactive current, which on a lot of radial distribution feeders will cause power quality issues. So kind of key takeaway, we're stuck with that inrush attribute of an induction machine. And another key takeaway, this is a reactive current problem. It's not a real power problem. Another key attribute of the induction machine physics that we're able to see from this table. So if we look at the starting voltage, a very common technique to feather the torque of an induction machine is to reduce the voltage on it. Unfortunately, that's not a very effective technique to reduce inrush current. So as we can see, typical reduced voltage starting is in that 70 to 80% remaining voltage range. And that still results in about a 450% or so reactive current inrush. So another important takeaway is that reducing the voltage on an induction machine only reduces the inrush current proportionally, which, because there is such a large inrush current profile in the first place, it's just not a very significant reduction. The key issue here is the starting torque has to be maintained on the machine. And so that's what's limiting the ability to reduce the voltage of an induction machine in practice.
Hey, Dave, why don't you flip back to that slide, and I've been kind of studying it as you've been talking. So the first thing I'll note is that at 1 per unit voltage, you have the locked rotor torque at 1.5. And from what my experience is that that would be good. That would be true for smaller motors, low voltage motors. But there's a lot of motors out there, especially at the medium voltage level, where that starting torque at 1 per unit voltage would be on the order of 0.6 per unit at starting. All right? Right.
Yeah, and so that is a good point. So this is a characteristic attribute of a NEMA type B motor, taken from a low voltage motor data sheet. What Paul is referring to is that certainly that lock rotor torque does change depending on the type of motor design that's used. And it's very common to see actually lower starting torques. And that just exacerbates that problem that I was explaining with reducing voltage. So make it more likely to, having to avoid a stall condition on startup is a critical issue that has to be avoided.
So if I look at the table, just to kind of help the listeners peel back what you did here, at 0.9 per unit voltage, 0.9 times 0.9 would be the voltage squared, so that'd be 0.81, and 0.81 times 1.5, which is the starting torque at 1.0, would become 1.22. So the torque output on the motor varies by the voltage squared. So 0.9 squared is 0.81. 0.81 times the starting torque of 1.5 is 1.22. So that fact means that as you reduce voltage, you're losing your torque by the voltage squared. And if your starting point is already 0.6 per unit because you have a larger motor, now your problem is really exacerbated at that point. All right. Yeah. So that's a key issue. You were talking about reducing the voltage on the motor too, and that's the characteristic of a reduced voltage soft starter too. Is they pull back the voltage to pull back the current, which in a sense makes things worse too because you're getting less torque. So there's a range where reduced voltage soft starts will work, but once you go up in motor size, or once you get far out on the network where the penis becomes significant, then the reduced voltage soft start simply does not work. So
exactly, and we'll go into that a little more in the applications. And it's also true that we often install STATCOM solutions where there already is a soft starter on that motor, just to kind of reinforce that idea that soft starters typically are not adequate to address the power quality issues.
Okay, great. All right, might as well we'll move on to the next slide. Great.
Sure, and so this is an example of a feeder, radial feeder with an induction machine. This data was taken about 8 miles down line on that feeder. The left graph shows a motor starting event. So the blue graph is the voltage on phase A during that motor start event. So that large inrush attribute we talked about on the slide is what is causing this large dip in voltage across the inductive impedance of that feeder. And we can see it's well below the target threshold that the utility set for ensuring there weren't power quality issues. And on the right is the same event on a different day, so, with the STATCOM now operating. And of course, the STATCOM provides VARs near the motor. And so just by canceling the VARs and providing those VARs right at the motor so that the feeder does not have to, we can see that the voltage drop on the feeder is now very much addressed, and that blue curve shows that with the STATCOM operating. There's a little bit of voltage drop remaining, and that voltage drop is simply due to the real power that motor is drawing, and kind of reinforces this idea that this is a reactive current and also can be addressed by a reactive current device.
Hey, Dave. So
Yeah.
what is the, and maybe you do not know this, but what's the 1 per unit voltage on this system for these graphs? Is it 13.2 or 13.8?
Yeah. So this is a system that's 13.2. So this is, we're looking at line to neutral phase A voltage here.
Okay, so 7,630 volts, 13.2 divided by 1.73, so 7,630 volts. Okay. So they're starting off, they're actually starting off a little bit low in voltage to start with.
Yeah, it looks like they are in, in cases. Yep. So we're not, in this case, we're not trying to impact their normal regulating voltage at all. We're in a control mode that is just looking for that VAR inrush event and then responding to that only.
So this brings up an interesting point, is that a lot of times when people are doing studies, they're doing their study assuming a pre-start voltage of 1.0, but the reality is on distribution systems from morning to night, as those distribution systems come up and load during the day, the voltage drops along the line. So the out maybe 8 or 10 or 15 miles out, the starting voltage, the pre-start voltage could technically be even as low as 0.9, because the electric utilities are only required to supply voltage between 0.9 and 1.1 per unit voltage. So your designers have to account for the fact that they might have a pre-start voltage as low as 0.9.
And that's a really good point.
Yeah. Okay.
So one of the things that is surprising is how expensive this problem can actually be when power quality issues are preventing an operation from operating as intended. Here's some examples of installations that we've done for motor starting. So the first example is a pumping operation that spread out over a few miles on a feeder, and multiple motors were being used to pump up from an underground aquifer. And every time, not every time, but if the system was heavily loaded to begin with, this particular industrial operation would experience nuisance trips when their larger motors were starting. So a larger motor would start, cause a voltage dip, and then trip off other equipment on that operation. And that could have a cascading effect, causing them to have to restart the entire plant. So a couple of those events in a month, and the overall annual cost easily adds up quickly there. Another example of a biogas processing plant. So this was a landfill that was processing the methane from the landfill, refining it into natural gas. Every single time that process started, the utility required them to manage the VARs so that it would not have an impact on their system. And in order to deal with that, they had to spread out their sequence over about 6 to 7 hours. And so they lost 6 to 7 hours of productivity. And by simply solving that inrush problem, they were able to get that plant up and running in about a half hour, save a substantial amount of revenue, lost revenue. Another example, and this one's quite common with quarries. Quarries tend to be in more remote areas on weaker systems. Here there was a operation that actually had gone off the grid due to some power quality issues previously and was relying on a diesel genset to run their motor operation. So the cost of renting that diesel genset and managing the fuel, and then of course having to deal with the O&M of that, added about $500,000 annually. So this is a real world problem that does have a cost. It's often hard to capture that cost up front and to become latent issues that need an easy solution. I think the other point is that the utility often loses in this situation too, because when these operations trip or have to fail, or in the last case, completely off the grid, the utility, of course, is not serving that energy any longer. So it's really a lose-lose situation, and this is really why we're excited to be able to bring a solution to the problem.
Hey, Dave, I got another question.
Sure.
Keep asking questions. So,
Good.
So there's obviously the industrial facility here loses revenue because of lost production. The utility loses money because of lost revenue because they're not selling power. So in the end, oftentimes who's paying for this solution? The solution is it's a medium voltage solution too, right? So it's going out a lot of times on perhaps a distribution system and not on the customer's primary bus bars within the substation. Who picks up the cost? How has that gone down in the past?
Yeah, so there's two models. The industrial can pick up the cost, or the utility can pick up the cost, and we've had both types of opportunities. When a utility has purchased the equipment, they have often realized that they're losing significant revenue. And so depending on the situation, the utility may actually be willing to purchase the equipment and solve the problem just on that alone. That was actually the case in the last bullet there. In other cases, which was driven, the top bullet example, the industrial actually worked collaboratively with the utility and us, and how that ended up being implemented was the utility actually signed an agreement with the industrial customer for enhanced service, and that meant a different rate structure moving forward for the enhanced power quality based on the STATCOM solution. And the utility then purchased it from us, but with an agreement signed with the end consumer to ensure that their investment would have an on it. So we've seen a third model, which is where the industrial is able to fund the equipment on their own as well.
So that's very interesting. You have a enhanced power quality rate structure or something like that. Maybe something that all utilities should consider is that they can serve their customers with a higher level of power quality, and perhaps it'd be another revenue stream for the utilities also.
Absolutely, and that was definitely the case in that scenario, and I think it was a win-win for both sides then. is a lot of these industrials actually do not want to own and operate the equipment. They just want their problem solved. And, you know, the utilities are great at owning assets, and they're great at maintaining assets at a high reliability level. So it's really kind of a win-win situation there.
Yeah, and it's medium voltage. A lot of industrials, they don't have a medium voltage technician available or lineman to do the work. So it makes sense that the utility take on that responsibility.
Yeah, and that's another great point. And so larger industrials will typically be able to the O&M of medium voltage equipment, but there's a lot of smaller ones, to your point, Paul, that becomes another issue.
Okay.
So we're just to kind of remind, we're talking about the problem and the motor starting problem and really what the cost of it is. And so we'll conclude this part of the webinar by visiting some of the traditional technologies that are available. Of course, this problem has been around for some time. And so there are some techniques that have been applied using conventional technology. So mechanically switched capacitors. So this is very specifically using conventional contactor technology to switch in and switch out so those caps are really good for motor run compensation, so steady state power factor correction. Generally speaking, the motor inrush problem is just too fast and dynamic of a problem addressed with a pure mechanical switch, and so they're typically not used in this application any longer. So we talked about reduced voltage soft starting. That, as Paul mentioned, the V squared characteristic of starting torque really makes soft starters challenging because in order, by reducing the voltage, that starting torque is being reduced significantly. In practice, that means that basically maybe a 20 to 30% reduction is all that's practically viable with a soft starter. That is only then a 20 to 30% reduction in inrush. So the soft starters are not adequate to address these problems, especially on larger motors. And then the other point on soft starters is there are also VAR, anything that slows down the motor or torque transient on the motor after starting can also cause a significant inrush of VARs on the feeder. And the STATCOM will compensate for any of those subsequent events that might be caused by the process causing a short-term torque transient, for example. Soft starters won't be able to address that issue either. And then VFDs. So VFDs definitely can be used to address inrush on the feeder. However, they tend to be an expensive option. They also need to be applied on a per motor. So for example, we talked about that site with 12 motors on a feeder. Each of those motors would have needed a VFD, which would drive that cost up quickly. And then the other issue with VFDs, especially larger ones, is that they do use rectified front ends, pulse rectified front ends. And so IEEE 519 compliance always is a concern with VFDs. And so if an additional filter is needed, for example, that'll add cost to the project with VFDs. And I think the overall point is that these tools really were not, they're not built and intended explicitly for power quality. These tools are actually intended for motor control applications. And then kind of a side product of them is, hey, power quality can be a little bit improved. So that's another kind of inherent limitation with the traditional technologies. Okay, so with the introduction of the problem, and just to kind of recap the key points there, we showed that this problem really is a reactive current problem. It's not a real power problem. And so we're going to introduce the principle of operation of a STATCOM, which is a reactive current device, a device that's able to supply reactive current. So makes it a particularly good match for this problem. So just briefly revisiting a STATCOM is a power electronics inverter that precisely controls reactive power. And STATCOMs can be configured to control either voltage, VARs on the feeder, or power factor on the feeder. The technology really had its origins in the transmission system, and STATCOMs are broadly adopted in transmission for utility-owned voltage regulation, as well as integration of renewables, especially in wind and offshore wind. And now their use is growing in distribution systems. And as we mentioned in the beginning, our distribution class STATCOM solution was launched in 2017. And that solution really is engineered from the ground up to be distribution class equipment. So we're showing in this slide here are installations in overhead distribution systems. On the left is a 15 kV class installation. On the right is a 25 kV class installation. And you can see that in the 25 kV class installation, there is a step-up transformer required with a riser pole, because the DVAR VVO power electronics natively operate at the 15 kV class. In either installation, it's what I like to call a two-dimensional installation, which means that the equipment fits within the existing utility right-of-way, which is really the key, kind of the key advantage of distribution class equipment, is that in order to install it, new land doesn't have to be procured, or valuable plant space doesn't have to be occupied, because it, just like other overhead utility equipment, it's able to be installed in the existing feeder right away. And it just shows the single line to be clear here. So on the left, that is the direct connection to the 15 kV feeder. And the three units there are each a single phase inverter. And that particular installation is a 1247 installation. And the rating of the STATCOM is 1 MVAR continuous. And as we'll discuss in a little while more, is that the STATCOM also can operate in a load at 130% of that continuous rating. It's particularly advantageous for this motor starting application.
Hey, Dave, these are single phase STATCOMs. So can you do single phase in a situation where you might have unbalanced voltage? Is that, does a VVO take care of unbalanced voltage situations?
It does. So the VVO can be configured to compensate for specifically amplitude unbalance. So in the distribution system, it is common that there'll be different amplitudes on different phases, and then it's a simple configuration at commissioning to tell the STATCOM to independently control each phase versus a positive sequence control mode. So there are two control modes possible: positive sequence and then independent phase. Okay.
So one other question: when you do for motor starting, is the feedback loop VAR flow, or is it based on voltage? Is it looking at voltage or VAR flow?
Yeah. So most of the applications look at VAR flow in the feeder, and then the STATCOM is simply commanded to cancel that VAR flow.
Okay.
And we have some single lines in this application section that will that will clarify that. But usually the best control mode is to use that line post sensor on the feeder current, and the STATCOM will directly compensate for the VARs that are measured in that feeder. So just revisiting kind of a high-level concept of a STATCOM. So from a power systems modeling standpoint, STATCOM looks like a current source, so it's specifically a reactive current source. And that's attractive because it presents a high impedance characteristic to the power system. So for example, if there's background harmonics present in the system, which often is the case at industrial sites, a STATCOM is not going to tend to absorb those harmonics, unlike a capacitor-based reactive device. The other thing is the STATCOM will produce pure sine wave output. So there's very little harmonic distortion in the output current of the STATCOM. And that allows the engineer applying it or specifying it to know that they're not going to have to come back and, for example, install a large harmonic filter to have to address harmonics compliance due to the device itself. Another key point that I mentioned is the overload capability. So because it's a power electronics device that controls current, the controller actually allows for a 130% overload output. That means it's 130% above its continuous nameplate rating to be applied for up to 1 minute. And that 1 minute duration can repeat 5 times per hour. So when we look at a motor starting event, which is typically, a long motor starting event would be 20 seconds, and they're typically much shorter than that. So this overload capacity being available for up to a minute allows engineers to specify the overload rating in these applications for motors. So it kind of helps to reduce the cost of the technology in this application even further. So this is just an example to reinforce the principle of operation here. So we know the motor current is primarily an inductive reactive inrush. So that's the one on the left. Then what happens is the STATCOM automatically applies the reactive capacitive current to cancel that inductive inrush, so that the net current remaining is a little bit of real power required to run the motor. And that real power, as we showed early on, is typically not going to cause a power quality problem. So it's usually a lot less than the reactive current. And then, of course, the feeder resistance is typically then not a significant factor in terms of causing voltage drop. Here's just a single line view of that same principle of operation. So the purple represents the inrush power characteristic of the machine. This is showing during an inrush event that the STATCOM is now providing 1300 kVAR of reactive current, and that's including the overload capability. In this case, there's about 1 kVAR left over on the grid during the starting event. And then once the motor starts running, the STATCOM will continue to provide VAR compensation, but the steady VAR compensation is much less, so then it automatically dials down its output. So it's very common that a STATCOM be sized. So our initial sizing idea is to cancel the VARs. If you're within about 85% or so of the VAR inrush, that is typically sufficient to to solve the problem. So for example, this 100 kVAR of remaining VARs, because the STATCOM couldn't quite cancel all of them, would typically not be an issue in terms of addressing the problem. So some key advantages that are brought by the STATCOM technology in terms of cost. So we mentioned site level protection. So a single STATCOM on a distribution feeder or STATCOM on a medium voltage feeder has the advantage that multiple motors causing power quality issues can be compensated. So if there's 2 or more motors, that single STATCOM will respond to any one motor causing an issue on the feeder. The other thing is the installations that we showed. The technology is designed with absolutely no moving parts. So it's 100% solid state technology. So there are no fans, there's no pumps. Really anything that's known to wear out due to mechanical wear has been taken out of the design, which allows for no routine maintenance. Because it's able to be installed on existing utility feeders or applications where plant space is hard to come by, that can be a nice advantage and bring the cost of the project down. And then, as I mentioned, because the STATCOM inverter technology produces sine wave waveforms, that allows us to avoid having to come back and solve a harmonics compliance problem, which, for example, can be a real issue when using VFDs at a site because they are pulse rectified. And generally speaking, a VFD will not comply with IEEE 519 on its own, so it becomes more of a site level study to determine whether it's going to be an issue or not. And those considerations are completely addressed with a STATCOM technology. And this just really summarizes what I just kind of went through in this section. So just to kind of recap, soft starters, while they're inexpensive, they're also having very marginal impact on the power quality issues. Larger VFDs can address these power quality issues, but we went through some of the limitations there. Specifically, they're not a site level solution. They have to be applied per motor. And then there's other considerations such as harmonic mitigation that can drive up project costs. And especially as these motors get larger, it starts to become advantageous in terms of cost. And then lastly, reconductoring really is not effective, again, because this is a reactive current problem. Reconductoring is really just going to address a real power problem.
So Dave, I think is to stress a point is you're talking about it being site level. You might get into an industrial facility and there could be 20, 30 RVSSs, reduced voltage soft starters. So when you're looking at a cost, you got to compare the cost of one VVO to perhaps 30 RVSSs. So there's some cost advantage having a site level solution versus a load level solution.
Yeah, exactly. And those load level solutions on a point basis can look very inexpensive, but yeah, when you zoom out and consider how much is required across the whole plant, then that's where the attractiveness of a site level system really shows itself. And then the other thing is STATCOM can also be programmed to address all power quality problems on the feeder. So depending on how we configure the control mode, that STATCOM can address not only motor starting issues, but other issues being caused by other devices at a plant, for example.
Yeah, there's ongoing costs too for those load level solutions. You have this, well, number one, the space, right? You get the space that each one of those RVSSs take up. You got the complexity of the actual device itself, the maintenance of that device. So you have ongoing costs associated with those devices versus a single piece of equipment actually outside the plant environment. So It seems to be a lot of advantages associated with the VVO product.
Yeah, exactly. And, we work with our customers to quantify those advantages and size up the right solution so that they can compare and make an informed decision on their investments as well. So we'll go through some application examples of how to apply some basic sizing guidelines and how to think of some very common site issues with the STATCOM technology when applying it for the motor starting application. So one of the considerations that comes up is the secondary voltage on a motor starting bus during startup. So what we're showing here is a single line diagram of an industrial plant fed by a medium voltage feeder. And are very typical voltages that would occur with a STATCOM solution. And so this is showing a case of a soft started motor. The secondary bus voltage would be above 90%. And that is typically managed at the time that plant was already architected and designed. So with a medium voltage STATCOM applied near the load, that will typically maintain right around 1 per unit voltage as the motor is starting. As we saw in the graphs, there's typically a little bit of voltage drop on the real due to the real power. And then all of these other utility customers, as well as other loads within the industrial plant, are protected by the site level solution. So couple points on the secondary voltage. In our experience, if you're above 90%, there's typically no issues on that bus. If there are other sensitive loads on that bus, it's generally very cost effective to simply move them over to a protected transformer on the does not have motor loads on it. And if these, you can see the ratio here is 1 per unit transformer to about 0.4 per unit motor. Up to about 0.5, 0.6 per unit is typically common sizing practice. If that secondary bus voltage is getting down around 85%, then we would typically recommend upsizing a transformer or adding another transformer to stiffen up that drop. But just general guidance that 90% or greater is typically not an issue at all on a secondary bus.
My experience, Dave, has been to what I've typically done is no more than a 4% voltage drop on the primary and no more than a 10% drop on the secondary would be my basic design principle, with the understanding that the utility might not give you 1 per unit voltage. They might give you maybe 0.95 per unit voltage, which means the customer's voltage at the motor during starting might even drop to 85%. And most of the time, right, you see these torque speed curves drawn for motors, 85% is the value that they show. So that's how I kind of derived that 90% number as a target design value.
Yeah, great. And yeah, I would say in our experience as well, we see that 90% range is typically not an issue at all. And then the other thing is motor relays start to get set typically below 85% as well. So in that 80 to 85% range, you'll see under voltage trips start to get set. So that's kind of another practical consideration. So I'll just run through some examples here just to clarify how the product can scale up in its size as we larger motor. So here's an example on a 13.8 kV feeder. So the maximum amount of VAR output with overload with one DVAR VVO system is 1400 kVAR. So that that's driven by, again, the ability to operate for 130% overload for up to a minute. And sizing, again, we're trying to cancel the VARs drawn by the motor so that there's close to the VAR being sourced by that utility feeder. To extend up a little more, we also support a hybrid configuration, and this is a nice cost-effective way to get another 600 kVAR out of the dynamic capacitive capacity of the device. So basically, this configuration, what happens is during normal operation, the motor is not starting or running, let's say, and there's little to no load on the, let's say, on the facility. What would happen is the DVAR VVO would actually absorb 600 kVARs of inductive reactive current, so that the net VARs to the utility are still around 0. So it's canceling out the capacitive, the fixed capacitance that it's installed with. And during that motor starting event, the VVO then rapidly changes its output from minus 600 kVAR, swings up to positive 1400 kVAR, which provides a total swing of 2000 kVAR. Total swing that is used to compensate the motor starting. So that's a nice cost-effective way to nameplate rating up to 2000 kVAR for a little bit larger motor. Then there's no problem paralleling STATCOMs. So having two STATCOMs near each other, motor culprit load, allows us to extend up to 2800 kVAR readily. And then that same concept of using a hybrid, the basic design rule is to have one 600 kVAR capacitor bank up to one 600 kVAR fixed capacitor bank per DVAR VVO. If we were to apply kVAR cap bank here and then another one on the second VVO, that principle of hybrid operation can bring a 2 VVO installation up to 4000 kVAR. So that's kind of a review of how to scale the solution up pretty easily to larger motors. Paul asked a question earlier about what's the kind of the control mode used, and we do typically recommend what we call the feeder VAR control mode. In this control mode, what happens is the VVO controller measures the load side VARs, and so these would be the VARs drawn by the facility and the motor, and then the controller simply injects the opposite amount of VARs so that the net VARs seen by the utility is maintained as close to 0 as possible. So that's a very fast and a very robust control mode. Part of the robustness is that because it's not operating on utility voltage specifically, the DVAR VVO will simply allow the utility to set their voltage wherever it needs to be. So, you know, depending on where you are in the feeder, utility might want to run their voltage a little higher, a little lower. Control mode, we're completely immune to where that initial voltage set point is because the device is only operating on the load side VARs. And that same concept with the fixed capacitor in a hybrid configuration means that that capacitor has to be located between the STATCOM and the load. So that's a key point in implementing the hybrid solution. So we provide some quick tables for reference. We also have an application guide on the topic of motor starting that really goes through more detail than we've gone through in this webinar, and provides these same tables with some more detailed explanation. Just briefly, what we're showing here is a lookup table that allows an engineer to look up the motor that is causing the problem. So that's on the leftmost column here. We introduced this idea of apparent motor size with the solution. So the STATCOM cancels out the reactive power during crush. It actually has the effect of making that motor look smaller than it is. And so values in this table are what we call the apparent size of the motor given the solution that's installed. For example, if we take this 700 horsepower motor with 2 DVAR VVOs, that will have the effect of making it look like only a 110 horsepower motor. And then the green cells are the cells where application can be expected to really robustly address power quality issues due to the motor starting problem. This table here is showing an example of motor sizes that do not have soft starters on it. This table on this slide shows it's the same idea, except have a reduced voltage soft starter on it. So with that reduced voltage soft starter, the DVAR VVO, which does reduce the inrush by a little bit, that allows for higher power motors to be addressed by the same configuration of DVAR VVOs. And allows us to get up to, with 2 DVAR VVOs and 2 fixed capacitors, allows us to get up to about the 1500 horsepower range and really fully address those power quality issues due to that. I'll just mention too that for large motors, we do have a substation class STATCOM solution. So what we covered today with the DVAR VVO is a feeder, pole mounted feeder solution that extends up to about 1500 horsepower motors. For larger motors, our substation class DVAR is also able to be used. So we're talking about 2000 horsepower plus motors. And then, of course, NEPSI has a solution called ActiVAR for even larger, several thousand horsepower motors. We have a couple case studies that kind of show our VVO device in action with these motor starting applications. So the first one I'll go through is a quarry where that induction machine was used to drive a conveyor within the quarry operation. So this particular quarry was located about 11 miles out from the substation on a radial feeder, radial above ground feeder. So the substation is down here at the bottom of the feeder, and then at about mile 11 is where the quarry operates, and then quality recordings were taken near the quarry as well as at a customer on a lateral a few miles away from that quarry. And what can be seen is that each of these significant dips here is actually directly associated with this motor starting problem that we're discussing. And as can be seen near the quarry, there was approximately 16% voltage dips, and on some meters that were on customers near the quarry, the dips were in the 10 to 12% range. This is just showing the nameplate rating of that motor. This is a 350 horsepower motor that was causing those issues. And so we were really able to use those lookup tables to determine that really one VVO should solve this problem. The utility that we worked with did ask for us to do a study in SIME just to confirm that sizing. And that's what we're showing with that circuit model. This just summarizes the problem and the amount of voltage dips that we're seeing. And here are the waveforms taken now before and after the DVAR VVO installation was installed. So the top graph shows reactive power, and as I mentioned, when these motors start, it looks like a step function of reactive power. So that's what we're seeing there with the red, and this is prior to any STATCOM on the system. So those bars are having to be sourced by the utility, and that's what was causing this dip at the quarry, and this is at the medium voltage side of the quarry. This is now showing with the DVAR VVO installed, and this particular application was just one DVAR VVO. So the red curve now, which was previously the VAR, which is the VAR sourced by the utility, you can see that those are now kept nice and near zero. That STATCOM is installed near the motor supplying those VARs now. And the associated voltage dip is approximately 2%. The STATCOM operates during that motor starting event. This is just showing a zoom to see the dynamic response. So, the STATCOM is, I'm sorry, the blue, and then the STATCOM is the orange. So you can see that idea of VAR cancellation with the speed of response of the STATCOM, and then the gray is the net left over. This is just showing zoomed in when that event first starts happening, and really shows that the STATCOM is really faster actually than the electrical dynamics of the motor. So that speed of response is actually being defined not by the STATCOM's limitation, but actually the natural electrical time constant of the motor drawing the VARs. So in this case, there was a very clear problem caused by a motor on a radial feeder, and that motor, very importantly, already had a soft starter installed. So just kind of reinforcing this idea that the VARs are starting to be there with soft starters. So our VVO was able to be installed quickly on that feeder to address the problem. It was able to be installed right in the existing right-of-way. So in this case, the utility customer didn't even have to develop their plant or make any adjustments. The problem was just solved for that. We talked about the attractive economics when there's more than one motor involved because the STATCOM can be used as a site-level solution. And so this last case study here will show a good example of that. Here is again, overhead circuit where the operator at this facility had about a dozen motors spread out over about a 4-mile section of the feeder. These motors were ranging from 300 horsepower to 1,300 horsepower. They were line start motors with soft starters installed again on them. And with those soft starters installed, they were still having the power quality issues, having downtime. Here's an example of a voltage on a secondary near one of the larger motors during a heavily loaded day on the primary feeder, and then as well as a heavily loaded secondary, and then a motor starting on top of it. So you can see in this case quite a low voltage dip here. This is about actually 70% remaining or so during that event. The total VAR loading of all the motors was approximately in the range of a little over 7,000 kVAR. Sorry, that's due to the largest motor starting on the system. These motors would typically be started not necessarily coordinated with each other. So it could be the case that two motors would be starting overlapping their inrush with each other. So in this case, we work with the utility to do another study, and we use SIME as the study package. This shows the distribution of motors on the portion of the feeder installed, and then it shows where we proposed to add STATCOMs to address the issue. And what can be seen here is what we did is we installed STATCOMs in pairs at 3 different locations along the feeder to match where the motors were being clustered. So here's 2 STATCOMs near the end of the feeder, compensate really for these motors. 2 STATCOMs here to be able to address these in the middle, and then 2 STATCOMs here to be able to address this cluster of motors. And in this case, we talked about the feeder VAR mode being the typical control mode. In this case, we worked with the utility to determine that actually the VAR control mode was the more appropriate control mode. And the reason is that these STATCOMs were not, motors were so distributed that it wasn't possible to have a STATCOM, a single STATCOM just applied on a radial feeder between the utility substation and the single motor. So because there were so many motors spread out, using that feeder VAR mode could not be guaranteed to pick out the right VARs from the right motor. So what we did to address that diversity of load and diversity of motor starts was to just use a voltage control mode. And that's here. So the dotted lines are during a motor starting event, measured at all the STATCOMs on that feeder. And then the solid lines are the injection of VARs from each of the STATCOMs in that motor event. And as we can see here, the dip in voltage is actually a little larger than what we showed in our previous case study, but we worked with the utility to determine that this was an acceptable. And these are just more waveforms of different events taken through our waveform analysis tool. So we're able to download these high-speed waveforms from all 6 sites and share the post-processed results with our customer. Another event showing how all STATCOMs are responding to this same event and coordinating with each other. One interesting note is, if a motor near the end of the feeder is starting, the STATCOMs near the end of that feeder are going to supply more of the VARs for that event, whereas if the motor starting near the front part of that feeder section we're starting, then of course the STATCOMs nearest to that would provide more of the VARs. And that's what's showing the difference between outputs here in these STATCOMs. So the STATCOMs nearest the culprit motor start are the ones that are responding with the most VAR output. And this is just another example of a motor starting event. And so this is a pretty complex problem that is causing really a lot of operational issues for this customer. Because of the nature of the distributed operation, it was very difficult to find a cost-effective solution. So the distributed DVAR VVOs was a nice solution for this customer because we could be installed on the existing feeder and use the DVAR VVOs to cover this distributed nature of the motors, as well as the time restrictions, or the fact that they did not want to have time restrictions on when any motor could start. The actual sizing solution required 5 VVOs, but a redundant DVAR VVO was installed because of the critical power nature of this. The customer really wanted the highest possible uptime and availability of this power quality solution. And then this particular solution was from the first time that we got the models and understood the problem, we evaluated and actually made the proposed solution and shipped all the equipment to them in about 6 months from the time they first approached us to the time that this was actually installed and operational. those are the couple of case studies that I wanted to share, Paul.
All right, great. So I was kind of making a list as we were as you were going through the presentation. So to my mind, I see a lot of different possibilities where this product applies. Sawmill operations, which have frequent motor starting or frequent locked rotor events. Compressor pump stations for oil and gas industry, whether it's part of a cryo plant or part of a pipeline operation. And remember, oil and gas, we have pipeline pump stations every 20, 30, 40, 50 miles. So it's a lot of motors being applied, oftentimes in very remote areas. Ski areas, I see, is another possibility. You have motor operations on long remote feeders. Distributed generation, quarry operations, and then in mine operations, maybe dragline shovels out along the line for dragline shovels. So just to name some possibilities.
Yeah, exactly. All of those operations generally use line start induction machines. So the possibility of power quality issues is, I would say, ripe in all those examples. So thanks for sharing those.
Yeah, and distribution feeders can get quite long. I mean, that's just the other thing that maybe some of the listeners don't realize, but they can get up to 20, 30 miles long. And when you have impedances in the 0.5 or maybe even 1 ohm per mile range, it can become significant, the impedance of the line. I mean, I think 0.5 is a good rule of thumb for the impedance of a 15 kV class equipment. So.
Yeah, exactly. And again, that amount of R's times that impedance is definitely going to be a problem.
Yes. Yeah.
So there's really no conventional. I mean, the other point is, conventional line regulation equipment that utilities have are just not fast enough to touch this problem. So a typical line regulator isn't even trying to respond for the first minute of a voltage excursion. So
yeah, they're fixing steady state voltage. That's all they're doing, right?
Exactly.
Yeah.
Yep.
So it's definitely a great product to consider for power quality, for sure. And all those types of applications I listed, and I'm sure many more would apply for this product. All right, so we're about up with time. I think what we can do is we're going to go to a question screen, and then we'll take questions from the audience, and we'll bring you back on, Dave, in just a moment. We'll give the audience a couple moments to ask their questions, and we'll come back and I'll read them off to you, and we can answer them together.
Yeah, perfect.
Great. Dave, we got quite a few questions here, so I'm going to read the question and we'll bring Dave back on to help answer these questions. So the first question is from Dan Dorshak, and hey, thank you, Dan. You are always on these Tech Talks, so we appreciate you coming on. So the first one is, please describe the basic features of the DVAR VVO STATCOM and how it differs from NEPSI's ActiveVAR compensation system. So thank you for the question, Dan. And you want to start off by answering that a little bit first, Dave, or should I start off?
Yeah, why don't you summarize, and then I can kick in some some additional comments. Yeah.
Great. All right. So Dan, the quick answer to that is the DVAR VVO is a power electronic device is using power electronics to create the VARs. There is no capacitors within that cap bank or within that DVAR system, the way you would think of it as in a capacitor bank. NEPSI's ActiveVAR solution is a fast-switching capacitor bank. It's a traditional capacitor bank with a transient-free switching device up front. So we're using standard shunt power capacitors, very fast, smart thinking relays, actually the 487V relay from Schweitzer, and a transient-free switching device to switch on stages and to switch them off. So it's the DS1M and the 487V that make that technology possible, but we're switching static capacitors in, where this DVAR VVO system is a power electronic device, and it's using power electronics to achieve what the capacitor banks are doing. So Dave, I don't know if you want to add to that.
Yeah, that's perfect. We typically see applications, our core applications are up to about 1,500 horsepower motors. And most of our installations are on 15 kV and 25 kV radial feeders. So whereas the ActiveVAR definitely is cost optimized for very large motors in the several thousand horsepower range.
Okay. We do have another question that, well, maybe we'll touch upon it now. So Mansour Nasabi has a few questions, and I'll kind of go through them one by one. What are the rating limitations for the STATCOM? And I'll add a couple of other ones. What's the reliability of the units, maintenance required, and the minimum voltage that STATCOM can operate? So these are some other questions that he had asked also. So maybe we can talk about those, Dave.
Yeah, sure. And I think maybe that question came in before we went through that section on ratings. So just briefly, the DVAR VVO distribution class STATCOM for one system for motor starting is able to provide 1,400 kVAR on a 13.8 kV feeder, and then we can scale that up to 4,000 kVAR using two VVOs in parallel with the external fixed cap banks, which is what we call our hybrid configuration. So that's a very common and standard way to address these. And with those two STATCOMs, they would typically be installed near each other. So one pole span away from each other, for example. And just practically speaking, when you get above the 4,000 kVAR requirement, you're typically seeing more of a substation application anyway, and that's where we would start to go to our larger DVAR or our larger ActiveVAR offering. As mentioned, to be clear, it is possible to continue to add DVAR VVO STATCOMs in parallel. So more than two can be added in parallel. It's just that, practically speaking, distribution feeders, 15 kV class, 25 kV class, it's just unusual to see that requirement arise. But we actually can go above that, especially if there's an advantage to keeping the equipment on that feeder right of way. And for example, there's a constraint in the substation.
Okay, and don't forget Tech Talk session 16, we had Naren on who explained what a STATCOM system is and went through that DVAR, their DVAR, larger DVAR system, that 4 MVAR and 8 MVAR system that they have. And then we had a Tech Talk session 26 just a couple weeks ago where we talked about hybrid STATCOM systems. So some other Tech Talks to go to. So let me proceed. There was a question about reliability, if you can address the reliability question, and what type of maintenance is required.
Yeah, sure. So on the topic of reliability, the equipment, the DVAR VVO equipment, was designed from the ground up for service in distribution feeders. And as part of doing that well, we literally stripped out all moving parts, and we stripped out anything known to require routine maintenance. So there are no fans, there's no pumps, there's no filtration systems. There's no, for example, batteries in the system that would need to be maintained. So it is truly a maintenance-free device. Things like routine visual inspections, which are done for all kinds of standard distribution equipment, including transformers. We would recommend those same visual inspections, but no routine maintenance. On the topic of reliability, one of the important things to understand about our STATCOM is that the lifetime of the STATCOM is not related to the number of operations at all. So this lifetime is more related to how much time the STATCOM spends at full output. So maybe a little simplified, but the analogy would be kind of similar to a transformer lifetime. If you run a transformer at its full rating for long periods of time, it's definitely not going to last as long as it will with a duty cycle or load diversity that keeps the loading over the course of a year or a day less than full, and then spending shorter periods of time at full output. So no relationship to the number of operations or the number of motor start events. That doesn't affect its lifetime at all. It's really only impacted by its time spent at or near full output. And of course, in this application of motor starting, it's generally a transient application. So the lifetime is excellent. If you're interested, we can certainly follow up with some actual field data on MTBF if that's interesting.
Okay, great. And what about maximum voltage? What's the maximum voltage the system can go to?
So in terms of the ratings of the core power electronics units, so we showed some single phase tanks. Each of those tanks is a single phase inverter. The maximum continuous operating voltage rating of each of those tanks, single phase tanks, is 8 kV. That's 8 kilovolts RMS. So which is basically allows a direct connection in 15 kV class feeders up to a 13.8 kV system voltage rating. And then on a 25 kV system, we showed that example where there was a step-up transformer used to be able to operate the VVO at 15 kV on the secondary of that transformer, but then operate and manage the VARs on the 25 kV feeder. So as long as the native operating voltage is kept at 15 kV, we're fully compatible. And we do support distribution voltages at 25 kV as well as up to 35 kV with the external pad-mounted step-up transformer. And then just to comment on, let's say, overvoltage tolerance. So the equipment's very robust. If there are temporary overvoltages, which happen during faults, for example, and during load rejections, the equipment is fully rated to ride through those types of temporary overvoltage events.
What about frequency, 50 hertz? Is it designed for 50 hertz systems too?
Yeah, it's a good question. So it's the same exact hardware, whether it's 50 or 60 hertz. So that's another difference between the solid state inverter technology and the passive technology. So you don't have to specify a 50 hertz or a 60 hertz system. It's just the same unit with the same ratings.
Great, great. So next question was in regards to modeling, SIME, creating a system model, what you would model with. Is there a model available? Could you talk to that a little bit?
Yeah, sure. So we do have modeling support for all of the common load flow modeling packages. So that would be Synergy, MillSoft, SIME. We also have modeling support for the transient solvers like PSCAD. So we do provide modeling guides for all of those modeling packages, actually. And we have a product page website where all of those modeling guides can be accessed and downloaded, and you don't need to register. So you can just go there and download it. Don't worry, we're not going to ask you for extra stuff there. And we'll maybe on this YouTube video, we can follow up with a link to the product page. And if there's any questions about where that product page is to, please don't hesitate to reach out. That's where we keep all the application resources for the product up to date for our users and our customers.
And Dave, you might not know this, but this is on the NEPSI site now too. So,
there we go.
Yeah, we got it on the NEPSI site too. So we'll be filling that out and making it deeper on our site as we move forward. There's a question about spreadsheet tools, and I don't think you guys have a spreadsheet tool yet, right? For this?
No, we don't. So I shared those tables, those reference tables that we provide, but that's really the only tool that we offer right now. So we, yeah, do you want to mention something about that, Paul?
Yeah, so we have a spreadsheet tool that we developed for ActiVAR, and the application is similar, but remember, ActiVAR uses capacitors, and capacitors, the output of the capacitor is based upon X of C, the capacitive reactance of the system. This STATCOM system works a little bit different, so we have to modify that spreadsheet tool. So we're going to be developing in the next, I would say the next month or so, we're going to modify that ActiVAR spreadsheet to accommodate the STATCOM solution, which it's a constant current, but the voltage can vary, right? So it's based upon, it's a linear relationship to voltage. So the modeling of it within Excel would be different. So we're going to develop that spreadsheet tool, and I think we'll have a couple different spreadsheets depending upon if the motor is downstream of the, say downstream of the VVO system at a different voltage level or at the same voltage level. So we'll have a couple different spreadsheets, and we'll be filling that out, making it very similar to the ActiVAR spreadsheet that we currently have, but designed for STATCOMs. So, a couple things just to, I think we forgot to mention during the presentation is the padmount, a padmount version of this. The present build out for this is to put it on an H-frame structure, right, in line with the overhead distribution system. But we have plans, especially with the purchase of NEPSI by AMSC, we're going to be integrating this VVO system into a pad mount version for placement where there's public access. So we're going to be following the pad mount standards and putting this into a load profile enclosure. And then there's also going to be a solution that's integrated for substation applications. So we have this coming out very soon. So if there's interest in that, please do get a hold of Dave or AMSC to discuss how to get some drawings and details on that product offering. And so Dave, any other presentations in your library or presentations for this STATCOM VVO product offering that you have?
Yes, so we have some standard presentations. One is just kind of like an overview of distribution class STATCOMs, where we kind of go over all the applications and the high-level principle of operation. And then we have a number of other deep dive, what we call deep dive webinars. This is actually one of them. So the motor starting application that we addressed today. And then we have one that we call accelerating renewables, specifically in the distribution system. And of course, interconnecting variable generation like solar plants, as well as areas taking on a large amount of rooftop solar. That variable generation is a cause of power quality issues and voltage regulation issues. And so in that webinar, we go through how a STATCOM can be readily used to cost effectively address those applications as well. And then we have one that we call power equality for ratepayers. So this whole idea of using a STATCOM, especially on downline feeder locations, instead of line regulators. So there's a lot of advantages to shunt power electronics voltage regulation as the primary regulation scheme on the downline locations of feeders. And from an overall standpoint, we've power quality is typically better near a substation, and the industry's kind of accepted that power quality is kind of lousy towards the end of feeders. Well, that trade-off no longer has to exist with the advent of low-cost shunt-based power electronics that can do this job. So a couple of other topics there that we're happy to put on webinars for.
Great. All right. So we're going to have you back at least a few more times in the coming
Awesome.
weeks and months, right? So maybe I'm going to do a rule of thumb slide that I like to do at the end, and I put together a few. So Dave, I'll just pop you off for a second there, and some rules of thumbs when it comes to this VVO product and the DVAR VVO. So when looking to mitigate voltage sags associated with large motors, motor starts consider the STATCOM solution, the DVAR VVO, and also the DVAR. Remember, the DVAR system is 4 and 8 MVAR and up. From there, it's a scalable product. So consider that for the larger motors, smaller motors, the DVAR VVO system. Also, remember that the DVAR systems are a system-wide solution. So they replace multiple RVSSs, multiple VFD drives, and therefore you get the cost savings associated with multiple devices. If you have multiple customers on the same feeder, you could be saving all those customers money. And this might be in West Texas where you have a lot of oil wells being drilled. The power quality out there is quite horrible. Also in North Dakota, on those long distribution feeders, same condition. So this VVO product is a great solution to take care of those types of situations. So when do consider the STATCOM for all dynamic voltage considerations, they would include distributed generation and also flicker from welder applications. So other places where you might want to think about using this VVO product. And finally, the DOTs. What don't you want to do? Well, don't connect large motors to systems without considering their impact on the neighboring loads, your other customers. Consider what the impact might be. So you got to do some type of motor analysis. The spreadsheet tool will certainly help in doing that. That will be our first line of doing some calculations to determine the impact of large motor starts on the distribution system. And also, don't assume, and I see this mistake all the time, somebody will install an RVSS on a system, and assuming that RVSS is going to correct the voltage sag issue on the utility grid. In fact, a lot of times RVSSs are installed and they're not going to make a difference on the system. Remember, RVSSs pull the voltage down to the motor to limit the inrush current. Well, on a very weak system, on these long distribution lines for which this VVO system is designed for, those RVSSs will be phased fully on and not limiting current in any way, and therefore they would not serve any purpose in reducing voltage sags. So they are the DOTs. In terms of, so let's go on. Remember, NEPSI's website has all kinds of information, including information on this DVAR VVO system and also the DVAR system. And remember to click the like button down below if you could, and also share with your colleagues. The certificate for this week is 716 to receive the PDH contact hours. And then finally, next week we will be off because next week is Thursday's Thanksgiving for us. So we'll be eating turkey about this time next week. And we'll be returning on December 3rd, and we'll be talking about rectifiers. And rectifiers are a harmonic producing load, and their power factor can sometimes be quite poor. We're hoping to bring on a rectifier expert, and we have not quite located one yet. We got some feelers out to find somebody, but rectifiers have poor power factor. We're hoping to be able to share with you how to calculate the power factor of a rectifier and also how to estimate what the harmonic currents are. These are all important inputs to harmonic studies, for which a lot of us on this Tech Talk are doing. And in the end, these systems require reactive compensation, and harmonic filtering. So it's very pertinent to what NEPSI does. These rectifiers, the ones that NEPSI are supplying filters into, can be very large, sometimes 20 megawatts of power being consumed by those rectifiers, and they can produce a lot of harmonic current. Chlorine plants are one place. We had graphite plants and electroweaning processes. These are the types of facilities that we're supplying these rectifiers into. And there's something new, and that's electrolysis. Electrolysis in the renewables area, where you're converting water into hydrogen to produce green hydrogen. So next week we're going to, well, 2 weeks, on December 3rd, we're going to create an electrolyzer here using DC rectification with a rectifier and show you how we can produce very easily hydrogen. So it's a very interesting new way. So that will be December 3rd. So we hope that you guys will come on board.